Hello, my name is Martin Karsten and I'm presenting our paper on user-level threading. This is joint work with my former PhD student Saman Bargi. The objective for our work is demonstrating that user-level threading is a viable alternative to traditional event-based programming. The motivation for this work arises from server applications that need to handle a large number of concurrent sessions, such as web servers or certain cloud services. Traditionally, these applications have been designed and implemented around the event-based programming model. Incoming events trigger the execution of handler subroutines. This is normally described as asynchronous control flow. In this model, applications must explicitly manage the state of each session. In practice, this sometimes means cascading event handlers, which is often termed callback hell. In contrast, the thread per session model supports automatic state capture and a synchronous programming style using blocking I/O operation. The open question is how much extra overhead is incurred and whether the performance can be competitive. In the past, the deterministic nature of event processing has been seen as an advantage over multithreading. However, to utilize more than one core, even event-based applications must run multiple kernel threads and thus also worry about synchronization. In fact, one way of supporting thread per session programming could be kernel threads. The problem is that kernel threads are typically limited to a couple of 10,000s. There are inherent overheads, but most importantly, scheduling is complex. The reason is that the OS kernel needs to satisfy fairness and control objectives for a diverse set of competing applications. In contrast, a user-level scheduler only manages threads from a single application and can be much simpler. Another key requirement is user-level I/O blocking. Application threads can then simply follow their execution paths, and the runtime system takes care of masking I/O latency to achieve good resource utilization. Before we go any further, let me quickly summarize the high-level takeaway from our work. User-level threads can provide competitive performance and in some scenarios even outperform lower-level event handling systems. Kernel threads are not bad either, but only up to a certain limit of concurrent sessions. For this study, we have implemented a nimble yet comprehensive runtime system that we call FRED. We demonstrate that our FRED runtime provides better overall performance than comparable runtime systems. With that, I want to give you a quick overview of the rest of this presentation. I'm going to continue by formulating a specific problem statement. Then I will give you an overview of the core design elements of the FRED runtime. Finally, we will take a look at some of the evaluation results from the paper before wrapping up the presentation. If you think about user-level threading as an extra layer between the event-based operating system interfaces and an application, the core question becomes, what is the minimum overhead of this extra layer? To address this question, we need to have a minimum viable and efficient threading runtime. We didn't find one and thus decided to implement our own. Most importantly, we wanted to evaluate a production-grade application with and without threading to compare apples to apples as much as possible. The approach here is taking an existing event-based application and adding the smallest glue layer to a threading runtime. We have done this from memcached, which is a well-known in-memory key value store. We have ported memcached to the thread per session model while retaining its internal state machine. This is truly a worst-case test for multithreading because we do not realize any of the structural benefits of thread per session execution. As I pointed out earlier, the key components of a user-level threading runtime are the scheduler and the I/O subsystem. For the scheduler, we can hope that simplicity leads to improved scalability and performance. However, the scheduler also needs to support load sharing across processor cores. This is typically implemented using work stealing and comes with an intricate race condition between searching for work and going to sleep. Most runtimes resort to some form of busy looping to work around that challenge, but the gold standard is clearly a scheduler that fully goes to sleep if there is no work. The central data structure used to manage processors and threads operates like a semaphore and is called inverse shared ready stack. A processor here represents a system thread running on a hardware core. The name of the data structure is derived from a shared ready queue, but the term inverse refers to the fact that the shared data structure queues processors instead of thread. Also, processors are kept in a stack rather than a queue. For the most part, threads that are ready for execution are stored in processor local ready queues. An atomic counter keeps track of the total number of threads ready for execution. A processor looking for work decrements the counter to effectively reserve a thread for execution. When no threads are available, the processor goes to sleep. When the counter is negative, it denotes the number of sleeping processors. Incrementing the counter leads to waking up one processor. Using an atomic counter is essentially equivalent to what's used to be called a benaphore. This is an old idea for making kernel semaphores faster by encapsulating them with an atomic user-level counter. The inverse shared ready stack scheduler requires only a single atomic instruction when the system is busy. More expensive log operations are only needed in underload situations. The I/O system needs to create a notion of user-level blocking to support synchronous control flow in user-level threads. In other words, when a thread attempts an I/O operation that cannot be completed, it is automatically suspended. Later, when the I/O operation can be completed, the thread is automatically resumed. This requires non-trivial interaction with OS-level notification schemes such as Linux's epoll or BSD's KQ interface. The basic architecture uses a global array to represent all possible file descriptors. Threads are blocked on I/O operations using user-level synchronization primitives. A polar component interacts with OS-level mechanisms to obtain I/O notifications and notify threads. A substantial part of our work has investigated multiple refinements of this basic architecture. This is all documented in the paper, but I don't have time to cover the details in this presentation. We've taken our runtime for a spin, along with many others. For a detailed list, I need to refer you to the paper. The first set of experiments uses a simple threading benchmark for testing locks and scheduling. Let me jump right to illustrating the results. This first test is a throughput test for a simple combination of locking and a work loop. The x-axis shows the duration of work, which translates into synchronization and scheduling intensity. The resulting throughput is shown on the y-axis. Higher is better. The results show that Micro C++, Mordor, and Arachne cannot reach the same level of performance as the other runtimes. Go shows some weakness for very short work loops, but eventually catches up with the other runtimes. However, performance is just one side of the picture. In the next experiment, we compare the efficiency of threading runtimes across a range of resource allocations. The x-axis shows an increasing core count, while the y-axis plots the average cost of executing each iteration of the experiment. In this case, lower is better. Micro C++ and Mordor again don't perform very well. Runtimes such as Arachne, Boost, and Qthreads use busy looping during scheduling and work stealing and have noticeably higher overheads. In summary, only Go, libfiber, pthreads, and our thread runtime show solid performance and efficiency. The next round of experiments is about I/O stress testing and is modeled after an industry benchmark from TechEmpower. We have included only those threading runtimes that support appropriate I/O blocking, but also add a best-in-class event-based web server as reference. Unfortunately, libfiber breaks under even modest I/O load and is thus also excluded from these experiments. I only have time to show one representative example here, a throughput test for basic I/O operations under different levels of parallelism. The x-axis shows the number of cores used, while the y-axis shows the measured throughput. Higher is better. Only the thread runtime delivers performance that is comparable to the event-based benchmarks. In summary, these benchmark experiments demonstrate that the thread runtime is the best candidate to evaluate the performance potential of user-level threading. Benchmarks are nice, but applications are the real deal. We believe Memcached is a good candidate for the type of evaluation we have set out for. We are not the only ones using this approach. Colleagues from Stanford have published a paper about their Arachne runtime in OSDI 2018 and also evaluated using Memcached. Let's take a look at some of our results. In a first experiment, we compare the throughput of the original event-based implementation of Memcached with thread per session variance. The x-axis shows a growing number of server cores and the y-axis shows throughput. Higher is better. The results show that thread per session variance can hold their own in this scenario, but only Thread achieves truly comparable performance to the original Memcached. We have also used this experiment to verify that our scheduling approach is indeed meaningful and effective. When using the Thread runtime with a simple shared ready queue, its performance clearly is reduced. This experiment was run with 1200 concurrent client connections. When increasing this number to 24,000 connections, not much changes, but Arachne loses pretty much any scalability. A central observation of the Arachne paper is that the load balancing in a user-level threading runtime can drastically reduce the tail latency of request processing. We have reproduced that scenario and show it here. In this experiment, a fleet of clients generates requests at a fixed total rate. The graph shows the 99th percentile of the resulting request latency on the y-axis. Lower is better, but also know that the latency is shown in logarithmic scale. As the workload increases, you can see how the tail latency increases. Both Arachne and Thread are able to sustain higher workloads and higher throughputs at lower tail latency. However, there are a few aspects that previous work has missed. For starters, the experiment is run at a moderate connection count of only roughly 1500 connections. However, at this connection count, using p-threads is in fact much better than anything else. So why bother with user-level threading in the first place? We'll get back to that later. Most importantly though, the question is, what actually causes the higher tail latency for the original Memcached in the first place? We have been able to pin this to interrupt processing in the Linux kernel. The details are in the paper, but one critical aspect is the number of Rx queues in the network card. The setup for the original experiment has fewer Rx queues configured than cores. We assume head-of-line blocking occurs and causes extra latency. If we change the setup to having more Rx queues than cores, the effect disappears. This graph shows the same experiment as before, but with corresponding changes to the networking configuration. The tail latency curves for all variants are fairly similar. However, if we increase the connection count to around 7500 connections, we can see clear differences between runtimes. Both Arachne and pthread based Memcached cannot handle this higher connection count, and their respective tail latencies increase much earlier. With that, let me briefly summarize our work. We have developed a nimble yet comprehensive user-level threading runtime and demonstrate that user-level threading can be done with low overhead. There are scenarios where user-level threading might in fact improve performance over traditional programming, but this is not necessarily the general case. The earlier Arachne work might have been a little too enthusiastic about this. Our Thread runtime stands out among other threading runtimes in being the only one that checks all the boxes and provides superb performance. With that, I would like to thank you for watching my presentation. If you have any questions, feel free to contact me by email.